I'm lead Dandy. We have Cris Quintana. We're from Airbus, and we're here to talk to you today about project QDOS Lite. So, it's not responding. We have a speed. Just waiting for PowerPoint's not responding. Do you set up the usual business? Sorry? Do you have a roadmap to the usual business? Your PowerPoint? Oh, yeah. This is very laptop, yeah. Sorry. It's okay. Now we can talk. So we're going to talk to you today about QDOS Lite. So just a bit of an introduction. We'll first look at what we've done previously, namely a project called AirStart. We'll talk a little bit about the vision of our project. Then I'll talk about how the project will be delivered, and then Cris will talk to you about the more technical aspects of the project, specifically the design of the optical train for the pod, and then of the base station as well. Okay, so what have we achieved previously? So this is a project called AirStart, which is a collaborative project, and in particular, the bit that's of relevance to us here is the actual pod, which you see beneath the drone. So the idea here, this was a classical link, so you'll see that naturally there are a few differences to what we're doing now, but ultimately we could establish a link. We've tested it to 1.2 kilometers, and this is free space optics communications from the drone to a base station. So as I said, we tested at 1.2 kilometers with a usable data rate of 400 megabits per second. It was slightly higher before forward air correction. And we have the capability at the moment to test this up to 10 kilometers with the vision to be able to go significantly further if we change a few of the optics. So we'll show you a video towards the end of this presentation, and you'll be able to see that in operation. So today's project then, QDOS Lite, which is essentially quantum key distribution from a drone. And what Airbus are always interested in is low swap, low size, weight and power. And so the project will demonstrate quantum encrypted communications with eavesdropping detection, as you'd expect, between an airborne platform and a ground station. And as I said, we're really interested in low swap for these applications. So information about the project, we receive public funding from Innovate UK, so it's part funded. We started last year, December, as you can see, and it's a 16-month project, so we'll terminate April next year with a budget of £1.3 million. And we have 5 partners, some of which are in the room today. So we have QDOS, ID Quantic, Airbus, used to be Airbus Group Innovations, just been rebranded as Central Research and Technology, University of Oxford and University of Bristol. So I'm not going to go through the entire work package breakdown here for you, but ultimately Airbus will be leading the project lead, and also work packages 0, 1, 4, 5 and 6, and I'll give you a bit of an idea what's involved in some of those work packages. So work package 1 is really about assessing the scene, so the use cases and applications. What's the target for this technology? What does the user want? And in this case, clearly, the end user, as we see at the moment, is going to be Airbus, but there may be others. And so this will be led by Airbus, as I say, with support from QDOS and Bristol University. And the requirements will be translated into sort of system requirements and specifications, which you can be measured against, and we can assess the performance of the system accordingly. Work package 2 then will actually be led by QDOS with support from ID Quantic and University of Bristol. And that will really develop the low swap optically and electronically packaged QKD, as well as the software and the drivers required to fully control the QKD system. Bristol University will develop a robust version of their fast-gated detector system, which will be paired with the QDOS receiver system. And then, as you can see in work package 3, there'll be a lot of work focusing on the ground terminal, which will be done partly with University of Oxford, but with a lot of support from Airbus at the moment, which is something that Chris will speak to you about. As we'll see when we get to the video, the UAV maneuvers actually become quite important, because you can imagine, as we have faster translations, the tracking system must be able to cope with these. And that's something that we did experience in AirStart, and I'm sure Chris will be able to elaborate a little bit on what we've done to overcome the requirement for more fine tracking in the QDOS Lite project. So in work package 4, this is really one of the significant areas for Airbus and our development, and that's where we will really focus on the optical train for both the pod, and we need to obviously think very carefully about how that integrates with the optical train on the base station. So this is why you will see quite close collaboration between University of Oxford and Airbus when it comes to this. So as I've mentioned, there will be a new fine tracking system. When we had the AirStart project, it's purely, let's say, one-way communication. We've got a ground station, we use GPS to identify, let's say, with as much precision as we can, the location of the drone, and therefore the location of the base station, and we essentially have to point and direct the laser towards that base station, and then we can transmit. Clearly, as Chris will explain to you, that won't be the case when it comes to QDOS Lite. So, work package 5, this will be led by Airbus again, with support from QDOS and Bristol University and Oxford University. And this will be where we carry out the testing of the system, both on the ground and on the UAV. So we'll have to do, as we did with AirStart, lots of ground-based trials initially to establish that the system functions as we anticipated it would, and then we'll advance to airborne trials And these trials can be done in two ways. One is from a hexacopter, which gives us a lot of flexibility because we don't need really large airfields to do that. And the other is from spotters. And then obviously the aircraft is traveling more quickly. We don't have the ability to hover. And so we have to be able to cope with the translations in many different directions. And then work package 6 is really where we have a dissemination and exploitation. So this is things like conferences, publications and so on, but clearly those will happen throughout the course of the project as and when you see fit. So I'm going to hand over to Chris, and he's going to come and talk to you about the optical design of the pod.
Thanks, Luke. Thanks all for coming. So I'm going to start this part of the presentation, giving you a general overview about the tracking system and the free space optics section. So here you can see the system architecture where we have a drone and a base station, very similar way to what we had in our Star project. So in that project, we transmit data from the drone to the base station, and now in the QDOS Lite, what we aim to do is to add an additional level of security using highly integrated QKD modules developed by QETS. So their system has three main requirements to work in this, let's say, harsh environment application. So the first one is that we need to keep the QKD channel link losses below 25 dB. So their system is fiber-based. So we get a module there with a fiber connection. The photons go through our optical system, get transmitted to the atmosphere. And on the base station, we try to collect as much energy as possible and couple back into a fiber, single mode fiber. So we need to keep those losses below 25 dB. So the key contribution of those losses is the geometrical losses and the beam divergence. So if we might minimize the beam divergence, the footprint on the base station is quite small, and then we require a very high precision tracking system on both ends, right? So to achieve that, or to implement that, we are going to make use of two auxiliary beacon signals. So one of them will be transmitted from the base station to the drone, and another one from the drone to the base station. On top of that, we need to implement two post-processing data links. So essentially, Alice and Bob need to talk to each other mainly during the establishment stage of the protocol, although also during the QKD transmission itself. So we could implement that links using radio frequency, but in this project, what we are going to do is modulate the tracking beacons with the post-processing data links. So by doing so, the main advantage of that is that the weight and the power consumption of the pod terminal on the drone will be minimized. The last requirement is that we need a very high timing synchronization between both Alice and Bob. So we need to share the clock of one of the terminals to the other one. Again, we could use GPS or radio frequency, but we have decided to use the QKD clock as a reference on the post-processing data links. So on the transmitter side. So on the receiver side, we simply recover the clock using a clock recovery module and give that clock signal to the other QKD module. So just to sum up, we will have a QKD link or channel going from the drone to the base station that will use 1550 nanometers, wavelength of 1550 nanometers. Then we will have a beacon from base station to the airborne, which will have 1545 nanometers. This will implement the tracking beacon, the QKD post-processing uplink, and also it will share the clock. And then we will have a second beacon from the airborne to the base station. and again will transmit the beacon, post-processing, and clock. So just to give you an idea, the key problem there, the key challenge is to isolate beacons and QKD. So just to give you an idea, the power of the beacon, it's about 7 to 8 order of magnitudes higher than the QKD channel. So we have to be very, very careful about how do we combine that to not contaminate the QKD channel with the beacon signals. So now I'm going to talk a little bit more about on the design of these two terminals. So this is the optical terminal on the drone side. So we have decided to go for a 2 stages approach. So initially we will have a course tracking module, which is essentially 2 mirrors, movable mirrors in a periscope architecture. They will use GPS signal to kind of roughly point the optical beam towards the base station. So with this kind of modules or design, we get a very large steering range, but so it is always positive to provide flexibility of movement to the drone, but the precision is not very good. So on top of this system, we will have a second system, a fine tracking system, which will have a narrow field of view, but it will provide a high level of precision. So that is rough. The fine tracking system is what I show here in the picture. So this system has been designed in CMAX and is based on a MEMS mirror that looks like that. So you can see that it's very highly integrated and the aperture is quite small and it sits just there. So we have an aperture of 50 millimeters, so this lens down there, telescopic lens, MEMS, some relay systems, and then 3 different arms. So this one down there is the QKD, the quad detector, which essentially sends the angle of incidence of the beacon coming from the base station. So that information, I mean the output of the quad, is used to control the MEMS mirror to direct the light back precisely towards the base station. The second arm down there is the in-gas detector to detect the uplink post-processing channel. And finally, the top one is the fiber terminal from where we launch the QKD qubits and the downlink beacon. So again, here we have to be very careful with contamination of the QKD channel, and the fact that they're combining fiber, we warranty that by doing that the co-alignment between them is almost perfect. Right? So this is the next, let's say, next step. So that was, the previous one was just optical design. So this is just mechanical. So I show here how the whole pod looks like. So we can see the fine tracking, it's just there. We have used, this is the 50 millimeters aperture. So we have used some fold mirrors to improve the integration of the whole system. Then we have the course tracking module, is this mirror down there, and this one. So this mirror can rotate this way and also provides the tilt. And then the rest of the system, it's just batteries and controlling electronics. So the mass of this module has to be below 5 kilos, and the size is 200 by 300 by 600 millimeters. So one of those boxes will be this. That is the QKD module provided by QET. So it's a low swap design. So we can see that the QKD itself is just this. It's fiber frame, and what we can see here is the controlling electronics. So this system, it's currently it's about 150 by 150 by 40 millimeters, but I'd say it's likely it will get reduced. The mass is less than 300 millimeters, so it's battery operated, and it's fiber fed, as I have said, and it uses 1550 nanometers. Okay. So on the other side of the link, we have the base station, which is again some kind of, it's not a replica, but it's similar in the design to the pod. Here we don't have any mass power restriction that we had on the pod terminal. And here we have to receive the QKD, couple the QKD channel, couple the photons back into fiber. And also we need to detect the post-processing, the downlink post-processing link, and transmit the beacon towards the drone. So that part, that combination again is critical to don't contaminate the QKD channel. And to implement that, we have decided to go for a topology like this. So we will have a mirror just in front of the last lens, that is that one. So we avoid, by doing so, we avoid any back scattering created of any lens to be coupled back into the fiber and affect the QKD. So this design again, it has two parts, a coarse tracking module and a fine tracking module. I show here the fine tracking module, which has lens, an aperture of 100 millimeters, a field of view of plus minus 0.24 degrees. It has, instead of a MEMS, it has a positive mirror, which is coil actuated, some relay system, and again 3 arms like we had on the other end. So we had quad fiber for the fiber terminal for the QKD, and in-gas detector for the downlink post-processing channel. So the key challenge here, the aim is to maximize the coupling efficiency into the fiber. So that is quite challenging because we have to cope with the movement of the drone and also with the atmospheric turbulence. Again, next step is, previous one was just optical design. This one we have a little bit of mechanics. So I show here on this part there is the zoom lens, which has attached to it a CMOS lens, a CMOS sensor. It's a visible sensor, and that is part of the coarse tracking system. So the output of that camera is used to control this palm and tilt unit, which is a mechanical head, and all of this optical breadboard sits on top of the palm and tilt unit. So the coarse tracking just roughly points the optical system towards the position of the UAV, and then the fine tracking system just do the fine adjustments. So we have again the 3 arms, as we have said. We have a photo detector, 400 megahertz bandwidth, and APD, very sensitive. And also we have installed here a linear translation stage to have the capability to test the system within multiple ranges from 100 meters to 1.2 kilometers. So we need to readjust the focus of the whole system. And I'd say that is all on my side. And here we have a presentation about a video about the Airstar trials.
Okay, I just need to know the video. Okay, so it's just a very short video, but you will be able to get the idea of what Airstar was about. So this was conducted January this year. I don't know if the audio cable. There's not a great deal of audio to hear. It's a drone flying, and you can probably guess what that sounds like. Nonetheless, I'll bring it in. Okay, so we conducted this up at Pershore in Malvern. So the pod's just been attached. So as I said, it's a battery-powered module, so it had a mass of 3.7 kilos. We may be able to reduce that through part of this project. So the arms that you can see sticking out, those are the additional 2 GPS antennae in addition to the 3 that the drone has. And that allows us to position exactly where the drone is. We can do ranges up to 1.2 kilometers. At this point, we're actually 500 meters. The base station is quite hard to see on the screen. It's in the inside of the red circle. So that's where we're transmitting the data to. And as you can see, the drone, whilst it is pretty stable, it will move around with the turbulence. And so here is this is the actual laser. You'll be able to see the laser moving in the sky. And this is we've got the coarse and fine tracking systems. This is what the eye would see from the base station. So this is zoomed in a little bit from the camera. So as I said, usable data rate 400 megabits per second, which is after FEC was 625 previously. The raw data coming in, so about 2 watts of optical power. And this is made, let's say, safe to the user by beam divergence within about 15 meters Of course, we'd maybe have to consider that. But as far as we know, this is the first demonstration of optical communication from a small unmanned plane. So with that, I'd like to invite any questions.
Thank you very much. Do you have questions? Go ahead, John. You're first up.
I'll just start. What are the timescales for the course and flight tracking?
I mean, the timescale, what is the loop time or the bandwidth?
How quick do they need to move?
Well, the course tracking, it's about, let's say, hundreds of milliseconds. The fine tracking is the one that has to be very fast because it has to, let's say, the course tracking just has to point roughly where it should be, so the real work is done by the fine tracking. The fine tracking system has to be within 1 millisecond or faster. Now we're targeting about 0.5 millisecond loop time. But yeah, that is essentially the turbulences change up to 1 millisecond, so we have to go faster than the turbulence. So to warranty, to establish, to have a stable light coupled into fire.
Thanks.
Just to expand on your question a little bit, at the same time, the drone, we can move it up to 65 kilometers per hour in any direction. So obviously we have to go, that's what I was talking about, we have to be able to cope with that.
There's two more. I saw there. Yeah? Oh, sorry. Back there first.
Thanks a lot. Really cool idea. I've just got one question about it. From your perspective, what would be the most credible intercept resend attack that you could imagine on free space data being sent from the back and forth? Because I'd imagine most drones that would be able to, absorb the signal and send a new one would be quite visible at a distance of, say, 100 meters or, even a kilometer.
Yeah, I'd say good point of laser comms is that they block. We won't be able to kind of see it. But the point is of this system is that with a QKD system, if it is blocked, we will work it out. So if somebody intercepts and re-emits, we will work it out. So we can stop the transmission. So I'd say probably the most dangerous attack could be some eavesdropper behind you, behind the base station. But I don't know, maybe you get
those photons would be lost anyways if they're behind the base station.
Say it again, sorry?
Those photons would be lost if they're behind either one of them in the protocol, regardless.
You can think about ATM, sort of, you put a fake thing on the cover, so you could easily think of this as now a drone system completely unmanned, and they put something on top of maybe the base station cover, where you're also comparing against it. Other ways of distributing, so you're comparing against a fiber network where eavesdropping is much easier to happen. Depends on what scenario you're comparing it.
Bear in mind that at this range, 1.2 kilometers, the beam divergence is like, the beam footprint is like 30 centimeters maximum, even less than that. So that means there's not much space to get to get behind, right? So.
I saw another question there.
Yeah.
I just wondered if you had any thoughts on kind of flight time, if that's in your requirements for this drone setup, because 10 kilos on a 20 kilo UAV is quite a lot.
Yes, it is, and we do that. So we have two drones that we use at the moment, these hexacopter types, and we know that we can do 15 minutes without problem. Of course, if we try and fly faster, that will reduce. And obviously, as you say, the more we put on there, then that's what we'll experience. But here, at the moment, we can comfortably do 15 minutes, 18 minutes without issue. That's what we previously done. We also carry, when we go to trial, we take 4 battery sets. I think it is, so we actually do multiple trials in a single day.
What do you see as the eventual uses of this kind of thing?
So I think that's, I appreciate it. It's a very good question, and for Airbus Defence and Space, that's a use case that they are still working through, and it's part of the work package. If you looked at work package 0 and work package 1, you will see in there that part of the things they have to do is the use cases, target applications, and those are normally developed through the program. So at the moment, I personally can't give you the actual end user use case, but I can tell you that it will be developed through this program.
what are your like target secret key rates you're hoping to put through for the quantum comps next?
So, I think that is a question for Kurt. I think was it hundreds of kilobits per second? I mean, qubits per second? I think that is and the main limiting factor in there is that the link losses that we have in the system. So the link gets diverged, so we add channel link losses, and that is why the qubit rate drops down.
One more question? I'll ask a naive one, because you showed it in Airstar, which looked optical as well. Why optics is RF enough? Airstar was an optical thing as well. Why optics? Why go there? Isn't RF enough?
Well, point is, yeah, it could be implemented with radio frequency links, but again, if we go into optics, we get lighter modules, which means obviously more flying time for the drone. We also add more security because the beam is highly directed, and also the size of the optical comps is going to be, I think it's about half of the whole radio frequency system. So it's always it's a win-win-win situation for this kind of applications where low mass, power, and weight is critical.
Well, thank Luke and Chris again.